Hello all, welcome to my channel. I'm back with another video. This video is part of the Spark internal optimization series. In this video, we will discuss about Project Tungsten. We have already discussed about uh, AQE. We have discussed about some other internals like dynamic partition pruning and stuff like that. So this video is part of that same series. If you have not watched the older videos, you can just check that out as well. So let's get started. So first thing first, what is why tungsten was needed? Before tungsten, Java was even heavily relying on JVM's object model. It still does, but with tungsten, it has some offloading. So what happened in this case is before tungsten was there, there were a lot of memory inefficiencies because of the Java objects that were getting created for every operation. And because we have large number of small Java objects, the GC used to happen a lot, and GC overhead was very high, and overhead plus GC pauses were also very high in Spark application. CPU inefficiency were also there, like because earlier without Tungsten, Spark was processing data row by row, and it did not utilize the modern CPU features, and hence Tungsten were designed to address these issues. So there are three major aspects in which a Tungsten engine optimizes the Spark's performance. One is the first category is the memory management and the binary format that it uses. So what Tungsten did was it shifted from Java object storage to a specialized in-memory binary format for rows, and this data was stored off it in contiguous memory regions. So because it was getting stored in off it, so it reduced the JVM overhead. And how it is stored like this, like you will have a null tracking bitmap at the beginning. It will say where all nulls are present. Then we have let's say if there is a data that needs to be this is a row like 1 2 3 data and breaks, so 1 2 3 gets stored in here, and then it will have an offset for the variable and data, and then it will say okay, what is the length of the data, and then it will say what is the actual data. So that way we store the data here. CPC data is stored here, bricks is stored here. So the size of bricks is 6, so it is mentioned in say here. Data size is 4, so it is mentioned in here. So this is how it stores the in-memory what you call unsafe row binary format. And this layout makes the Spark memory efficient and cache friendly. So if we want to have reuse the same thing, we hit the cache and we get it from there. So that helps optimizing the work. One example of one benefit of this is that if you see this here, the in-memory representation and on-disk representation of the same data, if tungsten is being used, so 3.8 MB is the in-memory, and when it is getting written to disk is the only 1 MB, almost 1 MB. So yeah, that's the optimization that tungsten provides. Because the size is getting small and we have less overhead, so this reduces the shuffle as well, because we are now only spilling I mean, we are spilling smaller data, we are exchanging smaller data because the data administration is better. So yes, this also, and also because there is no deserialization happening, so the shuffle is improved. One example where we see a tungsten's work is whenever you see a sorting, a common extensive expression in Spark. So you will see the on-wire representation is implemented so that the sorting can be done without having to deserialize the data again. So if you see, generally you will see sorting, there will be an unsafe row operator always. So that's phase one. And also the reason why the data here we are saying that the data on the disk is small, for that the reason for that is instead of using, for example, this is one example, there are certain other implements other optimizations as well, but for an int, instead of using a box integer of 16 bytes, Spark stores it in a 4 raw byte only, so that's how the size gets reduced. So this is on the memory part. Then cache-aware computation and code generation was also the next aspect of which Tungsten is trying to improve upon. And what it does in this is it basically creates a whole stage. So there is a process called whole stage code generation. What it basically does, it will fuse it certain operations on a same partition and create one single Java function to represent that. Instead of executing row by row for different operators, it will create one single function that runs everything in one loop itself. For example, like in a one SQL filter plus some selection can become a single tight for loop and instead of multiple iterators. So that helps in identifying on running the things more smoothly. And because there will be lesser and lesser function calls or operator calls, that reduces the what you call that reduces the overhead of running the system. This also has Tungsten also uses some algorithms and data structure to exploit the memory hierarchy. So that also helps in fixing some of the challenges that were there earlier, which were resulting in a cache miss. So now because the memory layout and the algorithms do are in sync, so the chances of cache miss is less. After this, there is a third aspect which Tungsten tries to optimize is the CPU. As we mentioned earlier, versions of Spark, we are not utilizing the CPU perfectly. For example, features like single instruction, multiple directives, single instruction, multiple directive was not being used, and loop unrolling, pipelining. So these were the new things, new features of which using Tungsten, Spark leverages this and combines it with vectorization. This reduces the CPU wastage that was happening, and hence it improves the total utilization of the resources which are present on the cluster. So how Tungsten works? Tungsten kicks in. I have sorted this thing. Spark will build a relation plan, then it will pass through optimizer. A physical plan will be created, and once plan is created, then the whole stage code gen kicks in. Tungsten then will create a fused layer, and that it will create a binary format of the data that is present, and then it will generate the bytecode and execute the code. So in summary, what it does, Tungsten fuses the filter and aggregation for a filter example. So Tungsten fuses the filter and aggregation into a single function and processes the data in a binary format and stores intermediates of it, hence reducing the memory and CPU overheads. So this is why Spark's Tungsten engine does help us in getting the uh, system up to speed. It reduces memory usage. It because there is lesser GC off it is being used, so lesser GC pressure is there. CPU efficiency is high because it uses loop fusion and vectorized operation, and the performance is predictable. Trade-offs, certain limitations of this is that it is very hard to debug the generated bytecode. It is not that much of human friendly. Still, some of the operations still run in JVM, so still it's not fully out of JVM issues. Always we cannot vectorize all those things, so it will fall back to the natural interpreted execution. And if we leverage too much of office data of it quota, it might cause leaks and we might not be able to handle it properly. Uh, uh, Tungsten is also now being combined with Arrow. So this means that the in-memory representation will also become such that it is able to talk to different languages. For example, Python to Scala or Java. That kind of translation will have give us more edge. Tungsten plus EQE is also the runtime adjustments happen based on Tungsten optimizations as well, and columnar processing with Spark 3.x, which is leveraging a lot of columnar storage. The CPU efficiency will even increase further. So yeah, in total, this was how Tungsten helps us in getting more performance out of Spark job. Uh, if you like this video, do share and have a nice day. Thanks.